The Shed, a cultural complex built above the railroad tracks on the west side of Manhattan, New York, is a building that behaves almost like a living organism, capable of expanding and contracting its body as needed. At the heart of it lies an unprecedented architectural concept, the movable shell. This massive 4,000-ton structure slowly glides along rails, transforming a public urban space into a performance venue and back into a plaza. An iconic scene that symbolizes just how far architecture can evolve today. We'll take a closer look at how the Shed's movable shell operates, exploring its structural mechanism, material technologies, and the ingenious engineering solutions hidden beneath its surface. The Shed's movable shell was designed with inspiration from gantry crane technology. Gantry crane is a freestanding bridge-like overhead crane that moves along a track or rail system. It typically features a single or double girder structure and is optimized for carrying heavy loads. This type of crane consists of two vertical columns supporting a horizontal bridge girder. Thanks to its robust structure, it offers exceptional stability and a high load-bearing capacity. In real industrial settings, it's a system capable of precise and powerful load handling, used to support materials weighing tens of tons with great accuracy. The Shed's shell is a bold architectural reinterpretation of gantry system, designed to stably support a large flexible structure as it moves with ease. During the design process of the Shed, the arrival of artistic director Alex Putz brought a significant shift in the direction of the project. He emphasized that the Shed should not be just a conventional performance space, but a more flexible and expandable stage, especially demanding that the space beneath the extended shell be capable of hosting large-scale performances and complex rigging operations, involving suspended or movable stage equipment. This request went far beyond a mere change in programming. The space beneath the extended shell, known as the Mech Court, had to function as a large-scale performance hall capable of accommodating up to 3,000 people. Its entire ceiling was required to operate as a structural deck, capable of supporting a wide range of suspended stage equipment. So the load conditions acting on this space became significantly more complex and demanding than those envisioned in the initial design phase. Heavier equipment loads, dynamic forces from performance rigging, and the shell's own self-weight. All these structural demands led the design team to adopt more innovative structural system to meet the challenge. The answer was the diagrade frame. To keep the massive shell both lightweight and strong, the structure employs a diagrade frame system, composed of a repeating pattern of triangles. As the name suggests, a diagrade is a structure composed of diagonal and grid, a triangular lattice formed by diagonal members. Unlike conventional structural systems, where columns and beams are arranged vertically and horizontally, the diagrade utilizes the geometric stability of triangles to efficiently distribute loads across the entire shell. This structure is composed of two key components. First, the vertical members feature trapezoidal cross-sections and gradually curve as they rise, following a smooth flow that extends seamlessly up to the roof. Second, the diagonal members connect the vertical elements with their cross-sections being thickest at the nodes and gradually tapering toward the midpoint. As a result, when viewed from the side, the structure takes on a distinctive form, appearing as if a complex curved surface is twisting. Each of these members not only fulfills a structural role, but also significantly enhances the sculptural quality of the shell's design.
This geometry it's very straightforward when you think about the load imposed on it, right? The gravity loads, there are vertical columns that all go back to those the wheel assemblies. So the vertical structures handling that. Wind loads coming from, we'll call it the east or west, these diagonals are taking those loads and making the frame rigid.
The steel diagrade frame that forms the Shed's shell is far more than a simple assembly of steel components. This frame, with its complex curvature and torsion, was custom fabricated in a factory based on precise digital design. Each member was made from high-strength steel plates with thicknesses varying from 10 mm to as much as 50 mm, depending on their structural function. In particular, the use of box steel sections provided excellent resistance to torsion and shear forces, while also ensuring good weldability and ease of construction. Once fabricated, the diagram members were loaded onto large trailers and transported to Manhattan, New York, during nighttime hours to minimize disruption. Upon arrival at the site, the members were assembled sequentially. Major connections were made using bolted joints instead of on-site welding, allowing for shorter construction time and improved maintenance efficiency. Spanning vast interior spaces without columns, maximizing load distribution efficiency, providing high resistance to lateral loads, achieving an optimal balance between lightness and rigidity, and enabling the structural realization of complex curved forms. Thanks to these advantages, the shed's shell is able to stand independently without columns and evenly distribute its total weight of 4,000 tons across 8 bogies, culminating in a globally unprecedented movable cultural infrastructure. In this way, the diagram frame that supports the entire shell as a self-standing structure was designed to withstand massive loads independently, without relying on the fixed base building. However, this shell is not meant to remain a static structure. It is designed to move in reality. So how can this 4,000-ton steel structure move across a plaza? Now let's explore the key elements that transform the shed into a moving building: its wheel system and mobility mechanism. Let's start with the wheels. This massive 4,000-ton shell moves back and forth along 2 parallel tracks located beside the building. The weight of the shell structure is supported by a total of 8 bogies distributed across 6 touchdown points. Initially, structural engineer Thornton Tomasity and kinetic design partner Hardesty and Hanover proposed bogies with a diameter of 3 feet. This was the maximum size that could be manufactured using standard train wheel production methods. However, due to the immense weight of the shed, multiple axles were required at each touchdown point. The architectural team DS+R insisted on having only 1 touchdown point per axle, and to achieve this, they preferred using wheels with a larger diameter. Larger diameter wheels offered the advantage of increased contact area, which reduced stress levels. And theoretically, this was a feasible solution. However, during the manufacturing process, it became clear that wheels of this size could not easily undergo the standard heat treatment typically used for conventional railroad wheels. In response, the engineer team conducted additional analysis and determined that the wheels could still achieve a 100-year lifespan with a more moderate heat treatment. This was deemed an acceptable solution, since these wheels move far less frequently than train wheels. They did not require the same level of fatigue design, making the reduced treatment standards acceptable. Ultimately, the team decided to use 6-foot diameter wheels and 6 touchdown points. Due to Alex Put's artistic vision, which included large-scale performances and complex rigging operations, the loads applied along the eastern axis of the shed became a significant structural concern. As a result, the bogie at the eastern edge was redesigned with a double-axle configuration. In the end, the system was finalized with 8 bogies distributed across 6 touchdown points. Of these, the 2 eastern touchdown points are each equipped with 4 wheels, while the 4 touchdown points at the northern and southern ends each have 2 wheels, meaning the entire shell is supported by a total of 16 wheels. The massive weight of the shell is distributed across the bogies, with a maximum roller load of 3,500 kN during movement and up to 4,000 kN when stationary. The load on each wheel pair is managed through a universal joint connection, allowing the system to automatically balance the load between wheels even when it's unevenly distributed. These wheels operate on an MRS-221 steel rail system. MRS-221 is an industrial-grade rail system known for its durability and commonly used in cranes and port handling systems. The rails are assembled using thermite welding, a process that melts steel around 2,500 degrees Celsius through a chemical reaction between iron oxide and aluminum powder. This creates a seamless metal joint, forming the 30-meter-long fixed track on which the shell travels. The rails are constructed as a continuous system using 8.66 inches, 500 pounds per foot heavy steel white flange members, designed to withstand the loads and deflections generated by the moving shell. Next, let's look at the drive system. Moving the shed's massive shell required a drive system that was both powerful and highly precise. At the heart of this system is the rack and pinion drive mechanism. However, this solution wasn't part of the original plan. Initially, a rope and pulley system was also considered as a potential solution. Ultimately, the rack and pinion system was chosen for three key structural and functional reasons. First, structural rigidity and precise controllability. The rack and pinion system is significantly stiffer than a pulley-based system and allowed for much more precise control over the shell's movement. In contrast, the pulley system posed issues such as sagging or slack in the roof due to variations in tension, making it less reliable for precise, large-scale movement. Such instability could have been detrimental to the smooth and reliable movement of the shell. Second, spatial constraints on the rooftop. The shed's roof had to accommodate not only the shell's movement system, but also a building maintenance unit for window cleaning. Therefore, the simpler and more linear rack and pinion system proved to be a more suitable solution for the limited rooftop space, compared to the complex pulley setup. Third, structural integration with the fixed base building. The rack and pinion system could be directly integrated with the upper structure of the fixed building, allowing it to structurally borrow lateral stiffness from the base building. In other words, instead of increasing the shell's own stiffness, the design achieved an efficient support system by leveraging its integration with the existing building. The rack and pinion system operates through a combination of a linear rack gear and a rotating pinion gear. As the pinion gear rotates, it pushes or pulls the rack, enabling the entire shell to move smoothly in a linear direction. The placement of the electric motor that powers the shed's movable shell was not just a mechanical design issue. It posed significant architectural and structural challenge as well. The designer wanted the motor assemblies to be visible from the outside of the building. They aimed to turn the moving structure itself into an architectural performance. At the same time, considerations of safety, maintenance, and risk damage also had to be taken into account. It had to be designed in a way that would prevent direct public access. Against this backdrop, engineers from Thornton Tomasity and Hardesty and Hanover proposed installing the electric motors on the upper part of the fixed building, on the roof. As a result, the shed's movement system is often compared to this analogy. It is similar to the way a shopping cart is pushed. The wheels on the ground rotate, but the driving force is applied from above, pulling the structure forward. The shell moves along two parallel tracks, with the slab drive responsible for the movement, equipped with 12 motors, each with 15 horsepower. The total combined output is 180 horsepower. This is equivalent to the engine power of a mid-sized SUV, highlighting the immense weight of the shell. The sled system consists of two precise synchronized devices, designed to electronically match the speed and position of the left and right side during the shell's movement, ensuring balanced motion. In addition, an essential auxiliary device, the centering system, operates on the top of the sled. This device ensures the structural alignment of the shell center during movement and effectively controls lateral stresses that may arise from wind loads or thermal expansion. With all these systems working seamlessly, the massive shell, weighing approximately 8 million pounds, can expand or contract in just 5 minutes. The actual speed of the movement is a quarter miles per hour. The massive structure moves slowly, almost like a living organism, and the shed functions as a precise and flexible movable art space. In this way, the shed's movable shell is not just an architectural structure, but a result of a digital design, high-strength materials, precise mechanical systems, and multidisciplinary collaboration. The scene of a 4,000-ton structure slowly moves along rails, freely reconfiguring urban spaces, is a prime example of how the built environment can evolve in a flexible and intelligent manner. Next week, the ETFE and the steel frame structure of the shed will be discussed. Thank you.